Give me 1 more minute and I will start. Good morning. Morning. So good morning, everyone. I'm happy to meet you in person today. And so, first of all, just a very quick in-person introduction. I want to know from all of you, where did you study during the bachelor? So, from Pakistan? Bologna. Bologna, civil, okay. Bologna, which program? Bologna, Sweden. Okay.
Indonesia.
Okay.
Egypt.
Okay.
Tunisia. India, Bachelor in Physics.
Okay.
Afghanistan. Ethiopia.
Okay.
India.
Okay. Then tempo. Ah, Trento. Okay.
Iran. Padova.
Sicilia. Sorry? Gibraltar. No. The last one. Where did you study your bachelor?
In Colombia.
Colombia. Okay. So, welcome to this course, Emerson. We start today doing an exercise, a very simple one that we develop to understand and to remember that the calculation of the stress state of soil is the base to develop any different problems that you have to face in geotechnical engineering. Okay? So, you may have to build or to design a wall, a foundation, anything, but remember that the starting point in any case is the stress state. Okay? So today we develop an exercise to remember something about that. But then, after that exercise, you have to practice by yourself, because I assume that you are able to calculate total stresses, effective stresses, and flow pressure. Okay? Because this should be something that you already know from your background. Okay? I'm sure you remember a lot of these. Maybe you have to, to remember, recall, and remember that this is very important. Okay? If you are not able to calculate the stress state, you will not pass the exam, for sure. Okay? If you get effective stresses wrong, then the exercise is 0 points. Okay? So the stress state of soil is something simple, but you have to have very clear in your mind what is the process, okay? The knowledge process, and which type of unit weight you have to consider in different parts of the soil. Okay? Yes. So, principle of effective stresses is the base, and physical properties of soils, in particular soil unit weight, and calculation of core pressures. Okay? I'm going to use the blackboard. Okay? Okay, let me see if you can see clearly. Okay, this is the scheme, the stratigraphy that we take into account. And let me have a look to the scheme together with you. Okay, so first of all, you have 3 meters of sandy gravel. Okay, you have not the unit weight of the soil as input data, but the density. Okay, in particular, for the first strata of gravel, have a look at the picture. You have the dry density, because looking at the picture, you immediately see that the groundwater level is here. Okay, it's 3 meters deep here. Okay, it means that if you have not capillary rise in the first strata, you have to take into account the dry unit weight of the soil in order to calculate the stress state. Okay? Then you have 5 meters of sand. Okay? And this value of density is a saturated value. Then you have 8 meters of silty clay. Okay? Okay, so assume for the stratigraphy in the picture, first of all, no capillary rise. Second point, you can assume hydrostatic conditions. For the groundwater. Are you happy with that? Is everything familiar? Otherwise, if this is not familiar or you do not understand something, just ask, okay? These are lessons, not an exam. So try to feel relaxed and ask, and that would improve a lot the quality of the teaching, okay? Because I'm here for you, okay? For you to understand and to be able, okay, to learn, okay, what you need as professional in your future. So please, okay, feel relaxed about that. Okay, but also remember that what I explain, what I say in lesson, then is something that I assume you will be able to discuss as an exam. Okay? That's quite standard, I think, at the university. But anyway, that's the report. Okay, so these are hypotheses, and they mean that, let me draw something here. So this is graven. And then we have sand. Yes. And then it's the final clay, let's say clay. Okay, here. Okay. Okay, the water is here. Okay. Since we have hydrostatic condition, we can assume that the profile of pore water pressure is that one with a constant inclination within the depth of your deposit. Okay, the inclination of the diagram of the pore water pressure is gamma double. Okay, unit weight of the water 9.81 kilonewton over cubic meters. Okay, so this is U naught, and this profile, this shape, the triangular shape, okay, is a consequence of these hypotheses. Okay? Okay. Otherwise, here, okay, the inclination of the diagram of pore water pressure, if we are not in hydrostatic condition, but you have C page, then is affected by the hydraulic gradient. Okay? So, the hydraulic gradient I is 0. Okay? I don't know if you are free tomorrow night. Yes? Sorry? These two conditions. Why? Because they are the simplest, the most simple cases that we can find. Okay? And so we start from the base. Actually, there could be something different in nature. You have to assume that I did investigations, that I go calls to find the stratigraphy, I put piezometers, I have a record of the pore water pressure in the site, and then I know that in this site, these are the conditions that apply. Actually, it's the first lesson, so I can start with something.
About
And when we assume this condition, we need to do tests, okay, and monitoring. Okay, so every site is different, as I told you in the last lesson, okay, because we are in natural conditions, so we study a real site, or we have to design a structure, so we need to do tests, okay. In this case, it's just an exercise in which I assume that I already investigated the site and I know the site and I know that. Okay? But we can discuss in the next example something more similar to the reality. I can tell you something if we have time about, I don't know, maybe the 2 towers in Bologna, the site. We have very good investigation there, so I can give you details and how we get a geotechnical model of the site, of the Adriatic Medicina Tower with the real site. But anyway, you need, in this course, you need the tools to solve and to simplify reality. Okay? So always remember that when you do a model of a real site, you have to extrapolate what you need for a particular type of technical work and simplify the reality, which is very complex. Okay? Okay? You never create a model which reflects the reality in all its details, never. Okay? You have to simplify and extrapolate what you need. Okay? Anyway, this is just an example, so I assume that I know that in this case we have this condition. Okay? Since we did a little break talking about seepage, hydraulic gradient, and condition, you have to know that tomorrow night I will be with my colleagues in the city center of Bologna, in Via Zamboni, Piazza Scaravulli, in front of Palazzo Poggi. We are doing activities for citizens, okay, not the ricercatori. Do you know about the event?
Yeah.
Okay, from 5 in the afternoon to midnight, we will be there showing little apparatus which explain some seepage phenomena related to creation of sand boils. Okay, so if you come, just say that you're a student of the course. We can show you something about physical models of sand boils, and we are also bringing the 1D apparatus, so a little 2D apparatus for children and students also, it's nice also for us, and a 1D apparatus, and you can create sand boils, okay? Thanks to, tomorrow night, Bologna City Center, I can, during the break, I will upload the link with the indication of the map of the position. Okay? So if you come, you can create sand boils, applying hydraulic gradients and deposit. Okay? But in this case, we don't have hydraulic gradients, not sand boils, fortunately. Okay, so this is the assumption. Okay. So first of all, I started from the second hypothesis, and you see that the immediate reflection of this is that we are able very quickly to define the water pressure regime. Why I wrote you note? Look at this helix. Note actually is 0. Okay. Do you remember what it means? Initial. Initial. Okay? Why initial? Because this is the initial stress state. Okay? And you have to remember that mechanical behavior of soil. So, mechanical behavior of soil. Depends on the initial state and on soil nature. Okay? And one of the elements that define the initial state is the stress state. Okay? Okay? But this is not the only one. Okay? There is a stress state, but then we will see, talking about critical state soil mechanics, that there are lots of more elements like the stress history, for example. Okay? Other things that we have to consider in order to be sure to have a good prediction of the answer of soil behavior. But stress state is crucial. Okay? Okay. Let's go on. Here is this is the ground water level. Okay? This is the ground level. And looking at this stratigraphy and looking at this hypothesis, in particular the first one, you have to remember that here, in order to calculate the stress state, you can consider the dry unit weight of soil. Okay? Gamma dry. While here we have gamma sat for total stresses and gamma dash for effective stresses. Okay? So in the first part of the layer here, total stresses, the vertical total stresses, for example, are equal to the effective vertical stresses, okay, while below these depth here, from here to here, they are different, and in particular, the effective vertical stresses are equal to the total minus for water pressure, okay, principle of effective stresses. Okay? Now, I started talking about vertical stresses. Okay? Vertical stresses, but you should remember that we also need the horizontal stresses for design. Okay? Okay. So actually the stress state should be calculated considering sigma dash V naught and at least sigma dash H naught. Okay? Where these are vertical and these are horizontal. Okay? How do we calculate the horizontal stress? Okay, let me start from that. Sigma dash V naught is equal to the saturated unit weight of the soil minus gamma W, which multiplies Z. Okay, this is the general formula, where these difference provide gamma dash, the effective unit weight of the soil, while sigma dash H naught is equal to K naught, the air pressure coefficient multiplying sigma dash V naught. Okay? Okay. So remember that if you need effective stresses, you can go immediately to this formula or start from the total and pore pressure values of stresses and then make the difference. It's up to you. While for the horizontal stress state, remember that you cannot, if you need to calculate the total horizontal stress, okay, you have to consider the effective horizontal stress and you have to add U naught. Okay? This is the only possible strategy to calculate total stresses for the horizontal direction. In fact, sigma H naught is not K naught, which multiplies sigma B naught. Okay, this is wrong. Wrong. Do not make this error. Okay? Okay. So general formulas here, which is something that comes from your background. K naught. What about this coefficient? Is it something that we know and we can extrapolate from theoretical approaches, rigorous approaches for soils? Do you remember how it can be defined for a specific soil? The earth pressure coefficient at rest. So first of all, say yes or no. Is its definition theoretical or empirical? Put up your hands for theoretical. Okay, thank you. Empirical? Okay, and the missing answer are I don't know. Okay, okay, no. Okay, it is empirical, its definition, okay? Because it is a function, it depends on the depositional process, for example, of the deposit and on the structure, okay? Remember that in the previous lesson we said that the soil is basically the answer of the soil is not isotrophic. Okay? Why? Because the deposition of a soil deposit, or soil layer, is the result of the environment, but also the fact that the force acting on the grains is gravity. Okay? So the vertical stresses which act among soil particles is different from the horizontal one. So packing of the particles is a function of the depositional condition, okay? As well as soil nature, physical properties, etc. So these K0, this earth pressure coefficient at rest can be calculated. Sorry, I write the equation here, okay, because there is no more space. K0 is 1 minus P dash multiply OCR with an exponent, okay, alpha. This is the Jackie formula. Which is an empirical formula. Means that it has been calibrated on data from different sites in which the horizontal stress has been measured, for example. Okay? So, as you can see, it is a function of P dash, which is the effective friction angle of the soil. Okay? Do not come at the exam and say, I don't remember its name. Okay? It's important. Okay? That you remember the name of this parameter. Basically, it's the most important soil parameter to define shear strength. Okay? Okay, so soil friction angle. OCR. What is OCR?
Over consolidation.
Ratio. Over consolidation ratio. Okay? Actually, I'm also doing the second part of the lesson together, okay? So we will be faster in the recall of the basics because I'm saying all things that you need, okay? On the second part. Okay, over consolidation ratio. It is the ratio between the pre-consolidation pressure of your deposit divided by the stress state of the soil in the point then that at the depth that you are studying. Okay? Sigma dash P is the pre-consolidation pressure. Okay? Sigma dash P naught is the geostatic stress. Okay? And this is OCR. Alpha is constant, it's about 0.45, 0.6, and this should depend on the soil type that you are studying. Okay? Okay. Okay, so this is crucial. Okay, the understanding of the stress state for pressure is something that you have to know. Okay, the fact that floor pressure is isotropic while the stress state of the soil element is not is something important to understand soil mechanics and then geotechnical applications. Okay, so please have no time to go back in depth into these concepts, but you read your book. Your book is simple now, okay? We did this effort because in the previous years we had a different type of book, which is brilliant and very useful, but maybe it was too complicated, okay? In this one, the first part describes all these concepts very easily. You can find definition, and I want to know at the exam that you are able to define these parameters, okay? So, please remember that during lesson, okay, I always try to tell you what you have to know, okay? Which is fundamental. Then, at the exam, in order to be able to do the oral, to discuss the subject, you must have an understanding of the subject, and so then it is up to you what you want to learn is something that is yours, okay? also related to the fact that maybe you want to specialize more in one subject or another, but there is something fundamental, and during lesson I tell you what is very important, okay, then all topics that we discuss here are relevant. Okay. So K-Not. Why I say that this is important? I say this because in a technical application we have to design walls, foundations, and calculation of earth pressure. Okay? Different design conditions are related to the evolution of stress state from the initial stress state at rest to critical condition, failure. Okay? We have to start from here. Now, I think this was the introduction to the exercise and something more. Let's go back to our calculations, okay? I will cancel that. My reference calculation. So we already have a diagram of core pressure. So what we used to do is to start from this point, okay, and we can say that here there is point A, then here we have point B, and here there is point C. Okay, as shown in the picture, which now is very small. I can enlarge the picture. Okay, point A, B, C are the depths at which we are doing calculations. Okay. Okay, so first of all, gamma dry is what you need to calculate the stress state in the first layer, okay? And you have the dry density that should be multiplied by G. And so you have here 1.5 for the first layer, which multiplies 9.81, and you have 14.72 kilonewton per cubic meters, and you can use this value to have the calculation of the effective, the initial geostatic vertical stresses in point A. Okay, so you have sigma dash V0, which is gamma dash, gamma dry of the first layer, which multiplies that. So we have 14.72, which multiplies 3 meters, which is the depth. Yes, 3 is the depth of the first layer. So just let me see the calculation. We have 44.16 kilonewton per cubic meter. Okay? So this is point.
Will this unit be meter square?
Yes, sure, 88. Thank you. And this is Q. Okay. Yeah. Kilonewton over square meters, which are kVA. Okay. And these are the same value of the total stresses at this depth. Okay? Okay. Now let's go on with the other depth. We have to calculate the saturated unit weight of the second layer, layer 2. Okay, so 1 and 2 stay for here, layer 1, layer 2, and layer 3. So the saturated unit weight in this case again is rho sat of layer 2 multiplying G. So you have 1.9 multiplying 9.81, and you obtain 18.64 kilonewton over cubic meters. And then here we are in point B. And this and in point B here you are at the depth of let me see 5 plus 3, you are 8 meters deep into your soil deposit. So the effective stress state in point B is given by the effective stress state sigma dash V naught in point A. So here is point A, okay, plus gamma dash of the second strata, which multiplies the relevant depth in which you apply this unit weight. Okay? So here you have 5 meters of sand. Why? It goes away sometimes. Okay, so here we are. Okay, so basically we have 44.16 plus 18.64 minus 9.81, which multiplies 5. Okay? This is gamma dash 2. So if you perform this calculation, you obtain 88.31 kPa or kilonewton over square meter. Okay? Is it okay? Actually, I adopted the use of gamma dash in the calculation of the effective stresses, but I could also decide to start from the calculation of the total stress. So another option is to calculate sigma V naught in point B. So this was the calculation in point B. Sigma V naught in point B, which is given by sigma V naught in point A plus the saturated unit weight of the second layer, which multiplies 5 meters over that. Okay, so in this case, using the data that we have and considering that for that you have to add 5 meters, okay, you have all the other data, you could obtain the total vertical stresses 137.36 kPa. Then you need for pressure. Okay, so in this case you have gamma W, which multiplies delta ZW in point B. So this is U naught in point B. And you have 9.81, which multiplies 5. So you obtain 49.05 kPa. And then you could obtain the same result you have above, so sigma dash V naught in point B has sigma V naught in point B minus, let's see, it goes working? No, it doesn't work. Minus U naught in point B. Okay? So 137.36 minus 49.05 is about, will be about 88. Okay? Okay. Is it fine with you? No doubts? That's fine. Okay, let's go past to the last point, point C. So, in point C, you can adopt the same procedure and obtain sigma dash V naught in point C equal to sigma dash V naught in point B plus the saturated unit weight of your deposit for the third layer, which multiplies Z. Okay, this Z in this case is 8. Yes, this is 8 meters. Here we have gamma sat minus gamma W. Okay, this is the effective stress of the layer 3. Sorry, this is a mess, so it's better if I write it better. Saturated unit weight of layer 3 minus gamma W. Okay, this is gamma dash. Okay, and this is the missing data, so rho sat of the third layer, which multiplies G. Okay, while this value was provided by the previous calculation, so we have 88, yes, exactly, 88.31 kPa. Okay, and the saturated unit weight, if you perform the calculation using 1.95 here, you can multiply by 9.81, you obtain 19.13. Okay? These are kilonewton and cubic meters. Okay? So you do your calculation. I'm not going to write it again. But let me see. Point C. Sigma dash is 162.8788. Okay? And this is the effective stress state of your deposit. If you need single values of total stresses and core pressure, you should add the calculation of sigma V naught in point C, which is sigma V naught in point V plus gamma sat of the third layer, which multiplies that. Okay, so in this case, you know everything. The bed in this condition again is 8 meters. And you obtain for this case 290.4 kPa. While for the U naught, you can use gamma W, which multiplies, you are here, so you are in point C here, so we have 8 meters plus 5 meters of water column, okay? So you have to multiply gamma W for 13 meters, okay? And you get 127.53 kPa. Okay? Is it okay with you? It's simple, okay? We take a little break. Please 10 minutes. Do not go take a coffee. I mean, you can take a coffee, but I will start again in 10 minutes, okay? So, take a rest and then we calculate the horizontal stress state and we'll see what happens if we have the variation of the ground water table, okay? If you have questions, I'll sit around here, okay? Yes.
I have an appointment with international desk and actually left the class. It's okay?
Yeah, sure, no problem.
The class will save in Panama?
Yes. I had the registration. Let me see if it is working. Yeah.
Yeah.
Should be okay.
Thank you.
Yeah, right.
Hi, I'm Elizabeth.
Very good. Nice to meet you.
Nice to meet you. My trains were all messed up this morning from Ravenna, so I just got here. I tried to take an earlier train and then it was canceled, so I had to wait an hour. And then the train itself sat for 30 minutes on the track. Can you just give me a little context on what we're doing? Yes. Just the vertical stress states.
Yes. We are doing an exercise from calculation of effective vertical stresses and horizontal stresses. Vertical and horizontal. Yeah. And for pressure. In this case, which is the bed skin, this one is standard. I can provide the description so you can try it. You can see. Yeah. So we have 3 meters of gravel. 3 meters of gravel. Okay, this is the ground level. Here. Okay, ground level. Then after 3 meters of gravel, you have discontinuity, so sand below. Go with it. The position of the water table, like line. Can you see also the yes? Okay. This one is the symbol that we adopt to show the position of groundwater table. Okay? So above the groundwater table is driven. We have no left rise, so core pressure are zero, not zero. Then we have linear increase water pressure when we are in 90% position. The unit weights of soils in order to calculate the initial system. Okay, which is raw density from which you get gamma. Okay. Usually I provide gamma. Yeah. Okay. 9.81. Okay. So then.
What is the
Yeah. No, it's okay.
what's the prime?
Effective. Okay. So we have total stress, which is the water pressure, and effective stress. Okay. You have to think that. Think about going to the beach. Okay. When you walk on the beach, your weight is hierarchy. When you go to take a bath and swim, you are not so heavy because of the water pressure. Okay, you're the same for soil when it is below the ground table. When you are below, grains are not so heavy as okay.
So that's why we're adding the saturated.
Yes, the dash means that these stresses are effective, are the real stresses between particles, right? That is the stress that particles will bring when you are using the groundwater. So you can calculate a total state of soil, which includes water, but also an effective one, which has excluded water. Let me show you the context in the here. With reference to the slides that you have, here is the part related to the explanation of the principle of effective stresses. Okay, can you see forward pressure acting between grains? Okay, this is the more plane. Okay, with the circle of stresses for soil and the representation of for water here. Okay, so in order to find out the stress state of a soil element below the water table, you have to consider total stresses, which include the saturated unit weight. Okay, saturated unit weight is the one of sun grains plus water. Okay, minus for pressure, okay, the pressure of the water, which is provided by gamma W in hydrostatic conditions. So effective stresses are gamma dash multiplying that. Okay, total stresses, which are sigma, this without the apex, is gamma sat multiplying that. And remember that the answer of soil is regulated by the effective component of stress. So it is very important that we consider.
So we've got total here, and then we've got
For pressure.
and then you subtract.
Yeah, I can subtract, or when we do it in a quick way, when you get practice on that, you can also directly calculate the effective stresses by using, actually here is dry, so here is something different because when soil is dry, everything is the same total and effective. But for example, here you can see gamma dash with saturated gamma dash you go straight to this formula, but it is the same as with that.
And
So
the
you see the same result.
saturated unit weight is
So the idea is that you start revising the concept related to physical properties of soil.
I've been studying the test.
Okay, great. Yeah. So the gamma part in particular, gamma is important. Okay, this difference, and then the of the So you have any background in architecture?
Not really. Well, I worked in construction for a long time. I was an engineer, so I kind of see a lot of this stuff. And I worked with a lot of engineers. Now I'm doing engineering. I mean, in the U.S., we have an undergraduate. My degree is not in engineering, but I took physics, structural engineering as like my. It's a little different. Yeah.
Where are you from?
I'm from New York.
Okay, so you wrote me about students.
Yeah, so I know someone who's a conservator from New York, and who's now for a couple of years in a row been bringing students from Yale, from the architecture program to do conservation work. So anyway, when I saw it in the slides, I just thought
That's
maybe you
interesting.
had
It's an interesting
done that.
contact for me because I really focus also my research on conservation from a geotechnical perspective, which is not completely standard. Also in Italy, I think, but especially abroad. I mean, in Italy, we are very, very careful in this. We do a lot. I don't see the same approach abroad.
Also, he's an architectural conservator, so not looking at
Yeah, I know. But, you know, in particular in conservation, you cannot avoid to merge okay? So maybe it could be an interesting, something interesting for you to share something of the next course in particular. And decide to follow the laboratory.
Right, you do that in Ravenna?
I do that. Last year there was Ilaria, my colleague, from I started a lot of years ago doing this course. Then she did the last 2 years, I think, and now I'm back to this course. Sometimes we have to rearrange our teaching. So I think this is very applied to study business if you really need that.
Yeah, I mean, I really wanted to do this class because I think it's so fundamental. Yeah, I'm not sure that when I go back to working whether I'll be actually doing historic buildings or not. We'll see. But regardless, I think having some understanding of it because I
know, but remember that the part related to historic buildings is only an application. Concept are the same for all different applications. The focus for historic buildings is more related to find the cause of problems of the structure, which is something that applies also to new buildings or to design properly the building if you are confident and you know what should happen if you do not consider something. So I think it's interesting.
On Fridays, I won't be able to come here.
I'm recording actually with Panotto.
So hopefully that's
I hope
fine.
it works. I think so, just let me know. Okay. But anyway, this part I can provide something to revise. This is also a book, okay, and in our book, so you can try by yourself at home if you are able to be independent. Okay, thank you. You're welcome. Okay, here we are. We can start. Okay. What is missing from this initial stress state? Horizontal stresses, okay? So, let's add calculation of horizontal stresses. Can I cancel? Cancel here, yes? Okay, in order to calculate the horizontal stress state, you need the earth pressure coefficient at rest for your different strata, okay? So, let me see where I did, okay. Here we are. So first of all, for strata 1, 2, and 3, you have to be able to calculate K naught, K naught 1, K naught 2, and K naught 3. If you look at your stratigraphy and your data, the input data that you have, you can see that your soil are not over consolidated. Okay? Why? Because there is not OCR in the list of parameters. Okay? Otherwise, you should have this parameter in order to define K naught. So we assume that soils, your layers are normal consolidated. Okay? So add this hypothesis. And C layers. NC means, remember, normal consolidated. Okay? What is the value of OCR for over consolidated deposit? One. Well done. OCR is 1. Okay? Remember, sigma dash P over sigma dash P naught. Sigma dash P is equal to sigma dash P naught for normal consolidated soils. Okay? Okay, so 1 minus sin P dash of the first deposit. Okay, so here it is. It's already given 0.45. Okay, so sorry. Actually, in this example, is already provided, and you have not P dash, but you already have in the data K naught. Okay, but anyway, usually when we do the exam, the exercises of the exam, we used to provide OCR and P dash. Okay. This is a very basic example in which this parameter is already provided. Okay? Remember that this is adimensional, has no unit, because it is the ratio between stresses. Okay? This is sigma dash H naught divided by sigma dash V naught. Okay, this is K naught. The earth pressure coefficient at rest. Okay, for those who are late, we had a discussion and a recall of these concepts in the first part of the lesson. Okay, so the same formula applies to all these layers. Okay. for different friction angle of the soil, different values of friction angle of the soil, and in the exercise these values are provided, and you have 0.5 for, no sorry, 0.5 for the second layer and 0.7 for the third one. Okay? Now, what do we have to remember for the calculation of horizontal stresses? That the horizontal stress state is not continuous with that. Do you remember that when we have an interface between different layers, we have a discontinuity? Okay? Why? Because K naught has different values. Okay? K naught changes. So you cannot have a continuous linear profile of horizontal stresses, but you have something which is discontinuous. Okay? In practice, I think Professor Gottardi, but also your professors of soil mechanics in your bachelor, told you that you never have discontinuities of the stress state because there are tangential stresses which make the profile continuous. It is curved, the real one. But in practice, we also simplify reality as engineers in order to be able to make calculation with a good approximation. So we create these diagrams which have these discontinuities. Okay, in the point where we have a integration of different layers. Okay, so if we remember these, and we look also at the stress diagram here. Okay, here we are. This is the stress diagram of our deposit. Okay, we have to start with the calculation of effective horizontal stresses along the depth of our deposit, remembering that at the interface we have not one but two calculations that must be done, just above and just below the discontinuity. Okay? Okay, so let's go. Sigma dash H naught in point A, so here we are 3 meters deep in our deposit. So again, point A. First of all, we calculate the horizontal stress state just above the discontinuity when we are in gravel, okay? And so we use K01, and you can multiply that for sigma dash V naught already calculated in point A. So okay, here we are. You have 0.35, which multiplies, let me see, 44.6. Thank you, 44.6. Okay, and we have 19.87 kPa. Okay, now I draw this little arrow here to say that we are above. You can use the symbols that you prefer to say that we are below the discontinuity. Then we can use the arrow in this direction. So just below the discontinuity, we have to use K02, because this is the horizontal earth pressure coefficient at rest for the second layer. and you multiply this value for the same stress state, which is sigma dash V naught in point A. Okay, so 0.5, which multiplies 44.16. And you obtain 22.08. Okay, so when you are going to draw the diagrams of stresses, remember that you have a quick increase of stress, of horizontal stress state, okay, at the contact between these two layers. Okay, we do the same going down at the interface between sand and gravel. So we are in point B. And we have sigma dash H naught in point B above the interface, and we have K naught 2, which multiplies sigma dash V naught in point B. So 0.5, which multiplies, let me go to the calculation to provide values. We are, yes, point B, 0.5 multiplying 88 to 0.31. You obtain 44.15 kPa. Sigma dash H naught in point B below the interface is K naught 3, which multiplies to the same value of effective stress. And in layer 3, K naught is 0.7, which multiplies 88.31. And so you get 61.82 kPa. Okay? Now the last point is point C, and then we stop, where you have sigma dash H naught in point C, which is K naught 3, which multiplies sigma dash V naught in point C. And you obtain 0.7, which multiplies 162.87. kPa, okay? And you obtain 114.01 kPa. Okay. Is it okay with you? Remember that what is very useful is to draw the diagram of stresses. This helps a lot, okay? Because you have your complete framework, okay? It is an exercise, the basic of exercise of the course of soil mechanics. The stress state diagram is represented here, okay? Actually, you notice that I focus more on effective stresses than on total stresses. Okay? We did calculation of effective stresses. Then I added the vertical total stresses. Is it important to define also the horizontal total stresses? Your opinion?
Okay.
Could be, if you have to consider the undrained condition, okay? Undrained condition, okay? If you have need to do a calculation in total stresses, because you have fine grain deposits, and then the short term is important, then you maybe it could be required to consider also total stresses for horizontal deposits. In this case, what you do, remember what I told you before, is to start from the effective stresses and add for pressure, okay? So sigma H naught at the different depths, okay, is this very basic calculation, okay? You perform first the calculation of effective stresses, then you add the U naught, okay? Remember for the fact that if you think about the value of K naught for water, it is always 1, okay? Why? It is always 1 for the solid. We have these two different continuums. Water is a continuum, soil grains is the solid part of your material. We superimpose from a theoretical point of view these two continuum materials is a superimposition, but the mechanics, okay, is different, okay? And in particular, where pressure is isotropic, okay? So pore water pressure has the same intensity in all different directions, okay? Remember that. So if we consider a K naught, ideally, a K naught for water, this is 1, okay? So you cannot use K naught of the soil for the total stress component, because you would need that you are adding a K naught which is not 1 here, okay? Okay, so you cannot, what I mean is that you cannot say that sigma H naught is equal to K naught multiplying sigma B naught, okay? Because inside here you have pore water pressure, okay, and the stress between grains. And if you do this, it means that you are applying the K naught of soil also to the fluid part of your material, okay? But K naught is not 1 for the grains, while it is 1 because the pressure, the horizontal water pressure is equal to the vertical one, so it's always 1 for water. Okay, so this is wrong, as I told you before, again. Okay? No, never do this. Okay, do that. Okay? When you have calculation of horizontal. Okay? Okay. So, can you see this diagram? Okay? The stress diagram here is the representation of the stress state for the wool deposit. We have done the pore pressure diagram here, and you can try by yourself, okay, to try to plot the diagrams with the calculation we have done. Okay? Try to do it. Start from there. Prepare the exam. Okay? See if you have problems. If you have problems, revise your exercise with the solution. If you still have problems, you come to me and you ask. Okay? To me, or you can write emails to the tutor as you wish, but start immediately to prepare the exam from that. Okay? Stress state calculation. I'm going to upload the solution of the exercise. I had a previous blackboard which is very nicely written down, so you can check if your notes are okay, and you can practice at home by yourself. Okay, I can do that, no problem. Okay, so you will be able to revise your understanding at home, but start to do it. Okay, because to prepare the exam is not sufficient. What we do during the lesson, you have to work too. Okay. Now, if you have time for tomorrow, okay, you can try to solve the exercise doing something, okay, to see, revise this solution, and then you can do that. Okay, so the idea is to perform the calculation again. Okay, it means do the calculation at least of the vertical stress state of your deposit, but rising the water table to the ground level. Okay? And see what happened to the effective vertical stress state. Okay? Try to make a comment about the comparison between the diagram of effective vertical stress state in this condition and the new one. Okay, and then tomorrow we can start just doing a very short comment about that and to discuss practical application. Okay, it's important. This is very important. Okay, so the only variation for the second part of this application is rising water table. Okay? What happened? It rains a lot. Okay? Like what happened last week here. Okay? And the groundwater table rises. Okay? Let's see what happened to the stress state and possible effect on the built environment. Okay? But do this by yourself, okay? Okay, so now this is the only exercise I'm going to do about the background, okay? Your background, your past knowledge of soil mechanics, but remember to revise as you can, as much as you can. The previous course of soil mechanics included the mechanical test, okay? So the meter test, direct shear test, and and triaxial tests at least. Okay. Also have a look to the tests that we used to do for defining physical properties, because they help to understand cell behavior. Okay. Okay. So some words, only some words. I think last week we arrived here. Did we talk about the odometer test? I was a bit like distracted last week by the flood. We didn't talk about the odometer test. I think we stopped here. We discussed this. I remember that. Is it correct? I remember this slide, and I remember talking about drain and undrained behavior consolidation. Okay? I also talk about that. I'm remembering. OCR, I remember defining that. And the odometer test is a laboratory test used in soil mechanics for the analysis of compressibility and stress history. Okay? So revise this part. Okay. Soil behavior at shear is something that we will discuss more in detail, talking about critical stage soil mechanics. Okay? Remember that the failure criteria for soils, the classical one, is provided by more Coulomb. Okay, here we are. So you really have to remember that soils are frictional material. Okay, so in general we can write that tau, the shear strength of a soil element, could be defined as a function of sigma dash tangent p dash plus c dash this is the more Coulomb failure criteria. Okay, where the stress state is provided by tau and sigma, while phi dash and c dash are soil properties, soil friction angle and the effective cohesion. Okay? This is easy. What is not easy is the real soil behavior, because this is a scheme. Okay? Okay? We will discuss this more in detail, but if we adopt the more plane for the representation of the shear strength of soil, you know that this criteria basically is a line. Okay? This is the failure envelope. Okay? So you can immediately see that in this plane, where tau is our epsilon and sigma is our x-axis, okay? This equation define a line whose inclination is P dash and the intercept is C dash. Okay? This is the classical failure envelope that we consider for the soil and that we define through laboratory tests, direct shear tests, triaxial tests are meant to define C dash and P dash. Okay? You are familiar with that, but you also know that this line is the representation of the soil behavior related to a particular stress state, okay? Because the real failure envelope is curved, is not a line. I'm sorry, you cannot see the blackboard probably, I didn't realize that. Can you see? No? I will move that. Okay, let's do something like that. Can you see now? Better? Okay. The real failure envelope is a curve which starts from 0 for most of the soil that we can find in nature. Start from 0 because at effective stress, at 0 effective stresses, the soil do not provide shear strength. Okay? Then it increases the shear strength and it is a curve like that. Okay? So it is a curve, not linear. What happens when we define a line for soil? When we define the line for soil, it is because we are testing our soil for a particular interval of stresses, okay, from here to here, and in this part of the real envelope, okay, this is our curve, and we can find an approximation of this behavior, which is a line, okay, a line with a specific inclination phi and an intercept c, okay, but this is only an interpretation for this stress interval of a behavior which in reality is something like that. Okay? So remember that we focus on a specific stress state when we define the failure envelope for soil, and we cannot use the same parameter to define some behavior for the wider range of stresses. Okay? So when you talk about cohesion in particular, you look at this parameter, pay a lot of attention because it is not something real, okay? It is a result of a mathematical model, okay, which is our line. The real cohesion usually for soils is 0. So this C dash is called intercept cohesion. Okay? Intercept cohesion. Pay attention because when you perform calculations, cohesion provides a lot of strength to your soil. But if you reduce the stress level at which you are working, for example, performing an excavation, then the answer of your soil at a reduced stress state, okay, going towards the origin, has a lower value of C dash, okay, because if you reduce the effective stress, the linearization becomes something like this, and then this, and then down there, okay, becoming 0, okay, here is the position. So pay attention to this parameter, not to overestimate your design, your soil properties, okay? Here you have some slides and pictures taken from your book. So again, my suggestion is to read them. Okay, I'm discussing during lessons the concepts. You can read them in the book and take out your notes of your previous course. If you have notes of your basic course of soil mechanics, you can use them. Okay, here is the concept of intercept cohesion. Then I think that it is better that I go more in detail during the analysis of critical state soil mechanics, because so you have a concept which is fresh during lesson. But you can do the revision of this by yourself. Okay? Now again, triaxial test, okay, is the main test, that the most important one that you can use in the laboratory to test soil samples. Direct shear test, which is something very basic but useful to provide an overview of soil behavior. Okay, now let's move to another concept, which is seepage. As I told you, the fact that we have hydrostatic conditions for soil affect the pore pressure regime, the pore pressure of water inside the deposit. When there is seepage, you have an hydraulic gradient which is not zero, it's different, okay? And you have seepage forces that act on the grains, okay? These affect the stress state of the deposit, and you should know, again from your background, how to calculate stress state when the hydraulic gradient is not zero. In this case, you should also know the direction of flow. So it is very easy to perform the calculation in 1D condition, okay? And you should probably remember the definition of total head of the water, pressure head, piezometric head, okay? And remember also the flow rate definition and the Darcy law, which defines the flow velocity. Okay? Then you have different possible conditions of water inside your deposits, and you should be able to predict them. Actually, this is one of the most difficult applications in the field. Okay? The fact that we should be able to predict pore pressures and their evolution when we build something. Okay? This is one of the main problems, and it is the reason why when you build a construction which requires a lot of attention, like a tunnel or a critical infrastructure in general, then in the design method you can apply the observational method, which means that you install monitoring system into your soil to see the evolution of pore pressure during works, and you can revise your design during works if you see that pore pressures are not developing as your prediction in the design. Okay? In this case, if you have monitoring, then you can revise design. So you can define different stages of design with steps in which you control pore pressure. Okay? And doing the exercise of that I suggest to do, the one this performing calculation, changing groundwater table, you can see why. You can see how you get what is the difference between stresses, and we can discuss that. Okay? Anyway, in the field, condition can be difficult to be predicted. Okay? If you come tomorrow night, you can practice with the 1D thermometer or the sand boil model. Okay, so here are the equation that you can adopt to calculate effective stresses when you have an hydraulic gradient I in your deposit. Okay, and also the equation for pore water pressure. Okay. As I told you, in 1D everything is simple. In 2D it's not easy to predict pore water pressure when you have two-dimensional flow or 3D. In these cases you can adopt the strategy based on the drawing of flow nets. Do you remember that? Yeah. Flow nets help because you can do them and you can predict pore water pressure in different points of your deposit, because in this case I, the hydraulic gradient, is different in different points of the deposit. While you have 1D flow, the hydraulic gradient is constant all over the site. Okay? In some cases, you really need finite element models to predict pore water pressure, because if you have not confined flows, then it's not possible to draw flow nets. Okay, let me see. I think I have finished, because I'm not discussing Bayesian constitutive models, because it means talking about elasticity, okay, linear elasticity, relation between stress and strains invariance, which is something that is more related to numerical analysis. You are going to do something, some of you maybe are taking the course of laboratory, the design course on technical engineering, and so those of you who are in this course can perform numerical analysis of technical problems. In this course, I'm going to use something related to the concept of elasticity, because it's basic, and also the concept of invariance. Okay? To draw stress path and to define critical state framework, but I'm going into detail of that from next lesson. Okay? So I have to leave the space to the other professor, I think. So for tomorrow morning, we start discussing more in detail the base of the critical state framework and the use of stress path for the analysis of stress. Okay? This is the very first part of the course, and it is propedeutic and numerical analysis. So when we go out from here, you can be called immediately to numerical analysis, at least you have a background with something related to that. Okay? Okay, so see you tomorrow. Here, this is for you, okay? And I'm going to upload also notes and the exercise later on, okay? Salve, sì?
Salve, il professor Gottardi ci aveva esplicitamente chiesto durante gli esami di riempire ogni formula con i numeri, e cioè lei chiede anche questo durante l'esame?
Ah, certo che sì.
Cioè,
se volete mettere il risultato, però se è sbagliato, è vero. No, sì, assolutamente.
No, perché lui l'aveva proprio espressamente chiesto.
Sì, ma vi farò vedere come vanno risolti gli esercizi, così, quindi mettendo dentro tutti i passaggi.
Perfetto, grazie.
Niente. Salve, buongiorno, spero di non essere stata troppo lunga,
no,
che
sono in
adesso sono le
anticipo,
11.
no, io quando vedo la circolare ultimamente è imprevedibile, per cui arrivo in anticipo al mercato. No, le dico, può lasciare, se non mi vedesse al cambio d'ora, può lasciarmi quello.
Glielo lascio di certo, sì,
Ecco,
ok.
così.
Riavvio così disconnesso.